So we were talking about this operation of convolution, which, as we mentioned earlier, it is one of the most fundamental operation of signal processing, estimation, detection, machine learning, communication, etc. It's a fairly simple equation to understand once you get your arms around it, but before that, it may seem little strange and little awkward to work with, but it is very powerful mathematical formulation. Essentially, we take two sequences, maybe in time domain, and when we say we are convolving them, we are actually applying this equation to compute the value of output for each value of the time index n. And this summation is over a dummy time index k. Basically, k gets summed out. K doesn't appear at the output. K is used to just index the terms of the summation. Now, x and h you can interchange, like what this equation says. You can make x to be h and h to be x, and you get the same output. So this equation is that way kind of symmetric. It doesn't care what comes first or what comes second. You know, unlike division, 5 divided by 2 is different from 2 divided by 5. However, multiplication doesn't care. 5 times 2 is same as 2 times 5. So same way, this is allowing the interchange of the variables, which comes first, which comes second. So this is also known as commutative property of the convolution, and it is that way similar to multiplication. But in terms of the notations, typically what happens is when you open up a textbook or read a paper, typically this terminology h here, it is more or less reserved for okay, so this h variable is reserved for what is called the system. And what do we mean by system is we will specify later on. And so the system, or sometimes it is even called a filter. Okay, so H is called the impulse response of the system or a filter or any such similar terminology. And then X is simply its input and Y is the output. So let us say why this is called, this H of n is called the impulse response, as we had noted down earlier. So for that, what I'm going to do is let us find so define X of n as 1 when n is equal to 0, and it is 0 otherwise. Okay, so this would be what we would kind of intuitively think of as an impulse. Because if I want to draw this type of signal as a function of n, so this is how it would look like. Okay, so this is the n axis, and let's say maybe this is -2, -1, 0, 1, 2, 3, etc. Then this one here, x of n, has a value of 1 when n is equal to 0, and everywhere else it is 0. Basically, the signal is not present. So sometimes this is called, in alternative ways, this is called an impulse, or I would say specifically a discrete time, dt impulse, or dt delta function. And it's sometimes also denoted as delta of n. Now, suppose if I have this xn as a delta function, let us see what yn becomes. So yn, so remember y of n is defined as summation of k going from minus infinity to infinity, x of k, h of n minus k. Now, when x of n is defined like this, do I need to do this summation over k at all?
No.
Yes, no. The reason is because all the values of x are 0, except only one value of x which is not 0. So this boils down to what then? Who can tell me what this will be?
H of n?
Exactly. See, when k is equal to 0, x of k is 1. And so this h of n minus k just simply becomes h of n. And for all other values of k from minus infinity to infinity, x of k is 0. So it wipes out this corresponding value of h of n minus k. And so what you are left with is just h of n. So the output equals h of n, and therefore h of n is called the response of the system to an impulse. It's called impulse response. This is not a new concept for you, actually. When you are playing a sitar or violin or any such musical instrument with string, if you just tap one time on that string, so from minus infinity of time to the current time, the string has not been tapped. Let us assume that. Then at this particular time, at present time, you tap it just one time. And then you don't again touch the string afterward. Then it is as if you excited that system, the guitar or violin, by an impulse. You pushed it one time. And then the musical note that you hear would be called the impulse response of that guitar. In your physics course, in the 11th and the 12th standards, you would have thought of and you would have worked with a type of force which is called an impulsive force. So there again, if there is a big box sitting and all that somebody does is they just push it one time. If the box is very heavy, then and the force that has been applied is very small, the box won't move. The impulse response is zero. Sometimes if it is a pendulum and you tap the pendulum just one time, it will start oscillating and eventually the oscillations will die out. Then the response of the pendulum to the impulse that you gave would be those oscillations. If there is a lake with a very calm surface of water, and you throw just one pebble, one stone, when the stone falls in the water, it will create the ripples. So the stone touching the surface of the water is the moment at which that impulse got applied to the surface of the water. And the behavior of the water surface then is called the impulse response. Okay, so the notion of impulse response is very important because once you have the impulse response h of n, maybe I should write it down here. If the impulse response is known, the behavior of this system to any arbitrary input signal x of n can be determined using the convolution formula. Right? So this is here we are taking a different viewpoint. The convolution formula that we have seen is just a math equation. And I think last time we went over how to calculate the output of that math equation. There, all we are interested in is doing the calculations, maybe even programming the formula for convolution in MATLAB or Python or Java. So that is one viewpoint that we looked at last time. The other viewpoint is more of an engineering viewpoint. It's a block diagram viewpoint. It's a viewpoint of some type of system which gets certain input and it produces certain output. Now, the remarkable thing about this property of such a system, the impulse response of the system, is that once you know the impulse response, if only thing that you know about the system is how it behaves when you apply an impulse, which is probably the simplest type of input that you can give to such a system, then by the virtue of the convolution formula, you can compute the output of the system to any strange shape of the input x of n. Right? So what the convolution formula says is, maybe I should also. So the reason why that is the case the reason why the convolution or why the impulse response is all that one needs or in mathematical terminology this is called sufficient. So why the impulse response is sufficient to obtain the output y of n to any input x of n is as follows. So y of n, I can write it as the linear superposition, okay, which is nothing but a fancy word for addition. Of delayed and weighted topes of h of n. So we remember we took this x of n as an example. So in that case, y of n will be 1 times, or let me write it this way. This is equal to x of 0 times h of n plus x of 1 times h of n minus 1 plus x of 2 times h of n minus 2. So this is an example of what I wrote here. This is an example when for x of n is equal to x0, x1, and x2. So if this input is made up of only 3 values, x0, x1, and x2, then this shows that the output is obtained by this impulse h of n. Here it is not delayed. That's why it's just h of n. And I weight it by x of 0. So I get some sequence. It is actually the impulse response. After it gets multiplied, all the values get multiplied by x0. Then what I do is I shift the input by 1 sample and then weight it by x of 1. And then shift it by 2 samples and weight it by x of 2. And I get y of n. For the example that we had here, when x of n is 1, 2, 3, what this becomes is nothing. This ends up being just h of n plus 2 times h of n minus 1 plus 3 times h of n minus 2. Okay. So to be absolutely clear, this equation is nothing but, you will see it is nothing but k equal to 0 to 2 x of k h of n minus k. This is our convolution formula. And what we are saying is that the output is simply the summation of the impulse response after it gets weighted by the coefficients of x. So the coefficients of x are known because that is the input. H of n is the impulse response. And so what this equation says is that if you know the impulse response, then you can calculate the output of the system no matter what the input is, provided that you know the impulse response. Is this fine?
Yes, sir.
Okay, so maybe we will take this example forward, and one more thing we'll do. So see, h of n is 113, right? Impulse response is 113 in this example. So I can actually compute y of n in this manner. So I'm going to write 3 lines. So this is going to be n x's, and I'm just putting out the markers. And this is 0, 1, 2, 3, 4. Remember in that previous equation that we just were writing, the first term is x of 0 times h of n. And h of n is 1, 2, 3. So it's just 1, 2, and 3. And it is not delayed. So I can just write it like this. And the reason I can write it like this simply is because x of 0 is 1. Sorry, 1 second. H of n is not 1, 2, 3, it is 1, 1, 3. So erase this. Right? Is this fine with you? What I did here? This is x of 0, h of n. X of 0 is 1, h of n is 1, 1, 3. The second term is x of 1, h of n minus 1. So who can tell me what this one will be? Or maybe I should write it down here that x of n is 1, 2, 3, and h of n is 1, 1, 3. So I already wrote x of 0, h of n. Who can tell me what x of 1, h of n minus 1, how can I draw it here?
From 1 second delay, 113.
Yeah. From 1 second delay, 113, except 1 second delay is correct, but what happened to this x of 1?
Magnitude gets double. Sorry.
Wait,
Times
2 to 6.
2 to 6.
Yeah,
2
so
to
it will
6.
be 2 to 6. I don't have enough space, vertical space, but you have to imagine that this vertical lines I'm drawing are twice as bigger. Maybe actually I should have drawn 1/4 line. Okay, and then finally x of 2, h of n minus 2. So what will that be now? First of all, it will have 2 seconds of delay. By the way, this n may not be in seconds, okay? It's just some data. It may not have even any time associated with it. So it's probably inaccurate to call it 1 second or 2 second delay, but fine, we'll just say that 1 unit of delay, 2 units of delay, etc. So this would be h of n with two units of delay, except it got amplified by
3 units.
3 units. So it will become 3, 3, and 9. And so now all I have to do is sum these terms. So the first I got is just 1, 0, 0. So I'll just get 1. Then I'll get 3. Then I'll get 8. And then I'll get 9 and 9. And then I'll get zeros. So y of n, which is the summation of these 3, becomes 1, 3, 8, 9, 9. So you can see here the linear superposition viewpoint of convolution. We are shifting the impulse response. We are kind of either amplifying it or attenuating it, essentially scaling the impulse response and then just adding them up. This is slightly different from what we did here. The calculations that we did here, there what we did was we actually took the impulse response. By the way, we fixed the position of x along the k-axis. So maybe I should say the main difference is that here we are directly working along the n-axis. Whereas here we are working along the k-axis. And in this k-axis, what we do is we take this x of k and freeze it. We don't move it. It is always at that position. Whereas for h of k, we first of all, we flip it around 0. And then, as we saw here, we keep on sliding it one by one. And then we just multiply the values which are on top of each other, add them up, and then we get corresponding value of y. So these are two kind of different viewpoints. Now, the second viewpoint, I thought use some very nice drawings, pictures, visualizations that some professor has come up with. And this hopefully will make you appreciate what we did in the previous class. Basically, this is that viewpoint where we flip the system impulse response h and slide it over the input vector x, which is frozen at a location along the k-axis. And you can see this demo at this Georgia Tech website. Here I have just taken the main pictures. Okay, so what is this saying? What is this telling us? That the input here, x of n, is all ones, right? This is what you see here. It is all ones defined over 10 samples, 0 to 9. The impulse response h of n, they somehow defined it as this exponentially decaying pulse. Right? And so in these pictures, these are drawn for the k-axis. But final output y of n is for n axis, y of n. We have to generate the output y of n. So that is generated over n axis. So what this picture says is that if I want to calculate the output y of n for n equal to -5, what I do is, first of all, I flip this exponential sequence. So it looks like this. I turn horizontally sideways. And then I shift by -5 units because I want to calculate the output at -5. So when I shift it, it goes towards the left and it looks like this. And now if I multiply the red and the blue, obviously I get 0. Nothing appears because whenever red is non-zero, blue is 0. Whenever blue is non-zero, red is 0. And therefore, obviously, if I add up all zeros, I get a 0. And so y of -5 is 0, which is this green dot. So now they calculate what happens when n is equal to 0. So now actually this h of n is literally flipped around. And just like what we saw in our hand-drawn example, the only thing that appears is 1. Everything else is 0. And so the first output is 1. If you want to calculate what happens at n equal to 2, you see that the impulse response, the flipped impulse response got slided by 2 units of time. Now you multiply the red and the blue. Because blue is all ones, the result of the multiplication is nothing but the red, except it gets zeroed out wherever the input is 0. And so you just get these 3 samples. So these are x of k, h of n minus k, product. And then once you add these 3 samples, you get the third output, y of 2. This is how you would do y of 5. This is how you would do y of 9. And it keeps on going. After n equal to 9, the output suddenly doesn't become 0. It takes some time before the output becomes 0. So this is how the entire output is computed. Okay, so this is sort of a visualization of convolution. One thing I want to say is that you should be able to see this very clearly yourself, that first of all, the input x of n can have, let us say, n samples, right? So it can be x0, x1, x2, up to x of n minus 1, total of n samples. The output, no, sorry, the impulse response h of n can have a length of m, which may or may not be equal to n samples. So the impulse response can be longer than the input, or it can be shorter than the input, or in the examples that we have seen, it may be exactly the same length as the input. It doesn't matter. M and n can be two totally different numbers. No relation between them. But in this case, the length of the output, the length of y of n in number of samples is going to be capital N plus capital M minus 1. So this is a formula that you can remember. So therefore, in the earlier example, where both x and h were having length of 3, the output was having length of 5. In the other example of Georgia Tech, both x and n were having length of 10. And therefore, the output length was 19. Okay. Now, just like the discrete time, this convolution actually applies even when we are considering continuous time. All that happens is summation becomes integration. So this is the equation for convolution when x and h are continuous signals. And the k got replaced by tau. The summation got replaced by integration.
હા વાંધો નહીં તો એમાં તમે એક વસ્તુ કરી શકો કે ટેબલના સ્ક્રીનશોટ પાડજો નાનકડો.
Kalp, if you are talking to somebody else, then please mute
ટેબલ
yourself.
ફરી ચેન્જ ટેબલ જોવું પડે મને પીપીટી મૂકો એમાં ટેબલ મૂકો. હા સારું બોલ સર ઇન્ટરનેટ નહીં આવે.
Okay. So you see that summation turned into integration. And this dummy variable k got turned into tau. So these are the two main changes. But the system viewpoint still applies. Now, this particular system, whose output can be obtained by convolution, maybe I should write it explicitly, whose output can be obtained using convolution. So only this type of system or systems which are called either linear shift invariant if it is discrete time, or linear time invariant if it is continuous time. And as we have said already, the defining aspect of such a system is the impulse response. So this is what we have done already. As seen earlier. In the continuous time, h of t is still the impulse response, but now the impulse is what is known as the Dirac delta function, CT impulse. This name Dirac is the name of a physicist who you have heard of. And he was the one to possibly first formulate this Dirac delta function. Now, I want to take just a moment in formulating this delta function because it will help us later on. So we detour segue into the Dirac delta function. So this Dirac delta function is defined for some argument x. Earlier we made it to be time t, but in general it can be any argument x. It can be not only time, it can be position in the mechanics. So delta of x is defined like this. First of all, delta of x minus x naught is the function located at the x naught value of x. Then there is this shifting property. Okay. So shift meaning to pass through a sieve and to isolate. Shifting property says that if you take any function f and do this integration with the Dirac delta function located at x naught, you get the value of f at x naught. Which is to say that if you just multiply f of x with delta of x and integrate from minus infinity to infinity, you get f of naught, f of 0. Sometimes this may also be called as the sampling property. Sampling viewpoint. If you want to sample this function f of x at certain value x naught, then this is what you need to do. You multiply f of x with delta of x minus x naught and integrate it. The output will become the value of the function at that x naught. It's the sample of the function. The other way, the other property of delta of x is that if you have this complex exponential, remember this is something that we have used earlier when we did up conversion, down conversion, when we defined discrete Fourier transform, etc. So one definition of the Dirac delta function says that if you take this complex exponential, exponent of either plus or minus j 2 pi xy, integrate it over y, then what you get is the Dirac delta function of x. Now, if you integrate delta of x from x equal to minus infinity to infinity, you get 1, which you can actually observe from this equation 1. If I make f of x equal to 1 for all values of x, I get this equation. But the output should become f of 0, but f of 0 is 1, because that is how I defined f of x. Then delta of x at x equal to 0 becomes infinity. And delta of x for all values of x not equal to 0, it becomes 0. And this part here, the second part, we can actually obtain from this equation number 2. Okay. Why is that? That we'll see graphically just in a moment. And then the last property of this delta function that we'll look at is called shifting property. This is different from shifting property. Shifting doesn't have edge in it. This is what we, a more familiar word, shifting. So what the shifting property says is that if I have any function f of x, if I convolve it with a Dirac delta function located at x naught, then the original function gets shifted to x naught. And this will help us for useful to understand the modulation theorem that we have seen. Of the Fourier transform. Remember, when we wrote the modulation theorem of Fourier transform, we didn't give its proof. We didn't try to understand why that has to be the case. But this here, shifting property will allow us to appreciate that modulation function. Okay, so let me just give an example. Let's say x naught is 5. And let us say that f of x is like this. It is defined over -2 to 4, and it has this particular shape. So if I do this convolution of f of x with delta of x minus x naught, then the output that I get is nothing but f of x minus x naught, meaning that the whole shape gets shifted to x naught equal to 5. X equal to 0 becomes x naught equal to 5. -2 becomes 3 and 4 becomes 9. It's like we took this f of x and we slided it rightward by 5 units of x. And this here, why convolution of f of x with delta of x minus x naught gives you this. This you can prove by using the formula of convolution and by using the property of the delta function. We won't get into the proof. Okay, so for positive value of x naught, when you do f of x minus x naught, it is f of x shifted to the right by x naught. And x plus x naught is f of x shifted to the left by x naught. So this is how we think of the shifting. Okay. And the last thing is that equation 2, remember it was this equation. This is the property of Dirac delta function, or the definition of Dirac delta function. Why this has to be true? Well, it has to be true because if I take the real part of this complex exponential, it is nothing but cosine. Imaginary part is nothing but the sine. And if I integrate them, then you see blue is negative, green is positive, they are equal in area, and so they cancel out. So when x is not equal to 0, the positive and the negative areas cancel out, and so we get an output which is 0. However, when x is equal to 1, this complex exponential has a value of 1 for all values of y. And so if I integrate it from minus infinity to infinity, if I integrate constant 1 over an infinite range, obviously I'll get infinity. Okay, so I think we have about 15 more minutes left. So I'll take a quick break and I'll be back in a few minutes. Okay, so few more viewpoints of the convolution operation before we move on to the next topic. One is that, this type of equation that is written as summation of some values which are getting multiplied. It can be converted into a linear algebra. And in this case, it becomes a matrix vector product. So the vector is the vector of input samples, x of n, and the matrix is having the impulse response. And you may be able to notice here that this impulse response, we have flipped it, like what was seen in that visualization by Georgia Tech professor. The reason I said we have flipped it is because if you look at the fourth row, it starts with the last value of h, which is h of 3, and then h of 2, h of 1, and h of 0. So this is the flipping part. And then you will see that different rows of this matrix are getting slided one by one. So this is the sliding part also. So the flipping and the sliding that we have seen earlier is a way to understand what the convolution operation is all about. It is all captured here in a matrix form. But once we write it as matrix vector product, again, we can bring back our two different viewpoints. One is that the convolution is a linear superposition of the column vectors of this matrix H after they are weighted by the weighting coefficients. So here I am taking the linear superposition viewpoint. I am taking the columns of the H matrix, weighting it by x of k, and then adding those vectors up. In some very specific terminology of linear algebra, what we can say is that the output vector lies, or the output vector is confined to a space which is spanned by the column vectors of the H matrix. Meaning that the output vector cannot be outside of the space of the columns of H. If columns of H are three-dimensional, output cannot become four-dimensional. It is this viewpoint, the linear superposition viewpoint, that we had seen just a while back, where we did actually the same operation, but we did it pictorially, right? We took the impulse response, we shifted it by one sample each time, weighted it by x of k, and then added them up. This is exactly that. And then finally, this linear superposition viewpoint can be thought of additionally as what? Who can tell me? Based on what we have done 2 lectures back.
Synthesis, sir.
Exactly. So Somin gave the right answer right away. So this is also can be thought of that the vector y is getting synthesized by the columns of H matrix. Synthesis coefficients are this input vector coefficients. Well, there is another viewpoint which is the vector dot product viewpoint. So here now we think of this matrix H as not comprising of different columns, but we take a row by row viewpoint of the matrix. And back over here, we were taking sample by sample viewpoint of the input, and we were getting the complete output in one shot. We are not having visibility into each sample of y. We are synthesizing the entire y together in one shot by adding columns of H. Now, in this other viewpoint, the situation becomes exactly the opposite. We don't care about the individual elements of X anymore. So we think of X as a vector, H as rows instead of columns. In this Y, we are not going to look at it as a vector, but we'll calculate each individual element of Y. So we are now looking at element by element view of Y, the output. And that is nothing but the dot product of a particular row with the input vector X. And so this is now the analysis viewpoint. We are analyzing X, and we are observing whether X is close to the first row, second row, third row, and so on. And when I say it is close to the first row, close to the second row, specifically, what I mean is whether it is directionally aligned. Because that is what the vector dot product does. It measures the alignment between the vectors. Because dot product is the magnitude of the vectors multiplied times the cosine of the angle between the two vectors. And so when the angle is 0, cosine is maximum, and then the output will be maximum. If the two vectors are 90° apart, then y of n will be 0. So this is another viewpoint. This we won't get into. This is simply the same thing that I say. The dot product is the magnitude of the two vectors, or the lengths of the two vectors multiplied times the cosine of the angle. Okay. And the last thing for today is, okay, we looked at the convolution operation in many different ways. We tried to understand it using different viewpoints. Now let us see where convolution becomes useful. So now we come back to our topic of modulation. You know, the modulation that we were considering first most, we said it's a simplified model. All that it had was constellation diagrams and those G functions. Then we made it a little more realistic by adding up conversion and down conversion. Still, what we have is not 100% realistic. The reason why is if I consider even a simple BPSK with, let's say, some 20 symbols that I'm transmitting one after another, so far we are just thinking of those symbols as either plus A or minus A. And they just go out in a stream like this. Now, today nobody transmits BPSK symbols like this. It is basically a sequence of impulses. Nobody does that. There are many reasons why this is not desirable. But probably one of the main reasons is that if I take Fourier transform of this type of signal, it will have unlimited spectral occupancy. Basically, the bandwidth will become infinite. Meaning, if I have to operate such a communication system, I will have to request infinite bandwidth from the governmental agency, which I will never get. Okay. So what is instead done is a BPSK symbol is what is known as pulse shape. What is this pulse shaping? First of all, we insert zeros between consecutive symbols of BPSK, and that becomes the input. The pulse shape itself is our system impulse response. Then the output becomes the pulse shaped output. You can think of this also as interpolation operation. So this is the original BPSK stream. Before passing it through the linear shift invariant system with impulse response h of n, I have to insert zeros between consecutive samples. So this is the zero inserted stream. And this is my one type of impulse response, which can be just a rectangular pulse. If I zoom it, it looks like this. The other type of impulse response can be a triangular response. Again, the length of the impulse response in both these cases is one symbol. And the third type of impulse response is called square root raised cosine impulse. And its length can be more than a symbol. See here, this pulse goes on over multiple symbols. And what is happening is that if I use this pulse, at integer sample durations, I get non-zero impulse responses. And we may see this later on, that this poses what is known as inter-symbol interference. Let us not get into it right now. But now I'm going to just take this input and pass it through the rectangular impulse, triangular, and the square root raised to some. So I experiment with these three types of pulse shapes and see what happens. In the rectangular case, this came out. Basically, each impulse got replaced by a rectangular pulse. So it became sort of a continuous in nature. So this is something that can be done by an actual hardware. You can have a pulse generator, and you just keep on changing the sign of the pulse. Impulses are hard to generate in a hardware, but this can be done. If I pass it through a triangular, this came out. Instead of rectangular pulse, now it became triangular. Each of these impulses that was there before got turned into a pulse. So remember, this first three symbols are -1, next three are +1, then again -1, and so on. And so that is what happens here. These first three are triangular pulses which are negative. Next three are triangular pulses positive. Then again I get a negative triangle. So each of the impulse got replaced by a triangular pulse. And the location of the triangular pulse is exactly the location of that impulse. And so if you think about it, what has happened is linear superposition of the impulses after they get shifted by the symbol duration. And in that linear superposition, we don't want to mess up. We don't want to create an artificial symbol in between two real symbols. And so that is why we had to insert zeros. If I didn't have zeros in between, and then I'll get some spurious symbols in between the actual symbols because of the linear superposition. And then the final output is the square root raised to 7. And this probably is the most friendly type of signal to be generated by a hardware. You see, there is no sharp discontinuities here. Unlike the triangular or the rectangular pulses, this pulse is kind of smooth. It is kind of wavy in nature. Okay, so this is the application of convolution at a communication transmitter. This is where we will end today's lecture.